Hi dear students, today we have come with a new video of class 10. In the previous part we have discussed about the prism and the path of light rays through prism. So today we will discuss a little more interesting thing, that is some application of refraction of light. Okay, so we will see what will happen when the refraction of light occurs. Okay, let's see. So first point that will be written as the change of depth. Whenever we have seen a vessel from the top with making an angle, we have seen the depth of the vessel seems to be decreased. Okay, so assume if it is a vessel, if we have seen at an angle, then it seems to be that the actual depth is not just like this. If you have seen it from the top, if it is filled with water, it seems to be like here. So the depth, it seems to be decreased. Just take that experiment, take a glass of water and see it from an angle, and you will feel that the depth of the glass seems to be decreased. Now the question has come, why does it happen and how we can able to find out that how much the depth is decreased whenever we have seen it from a height. Let's see. So for that case, we have to show you one experiment, though the experiment is shown in diagram. So assume it is a glass. Okay, so we have filled water up to this point. So if I'm talking about the depth, this is the original depth of the water. We have denoted by H. Clear? I'm taking one point here. Okay, and that point we have given a name, that is O. So if I have taken a point, so from that point there should be huge number of rays are coming to our eyes. Assume a ray that is coming directly in a straight line, that is incidenting vertically on the separation between two medium. There will be no deviation, it will go by this way. And if the light ray incidents by just bending little bit, okay, just I'm bending it little bit, then we have to draw a normal here, because as it has incident with an angle, it is the normal in. And for that case, as it is a denser medium water, and when it is incidenting and the joining between the two, this is the angle of incidence I. The refracted ray will be this. Okay, that is R. That is angle of refraction. Now, if a human being is just want to follow the path of ray by here, okay, so it is clear he cannot able to follow this bending path, because I have told earlier also that that is a characteristics of human eye, that we cannot able to follow the bending path of the light. We just follow the straight path. So if we follow in straight path, that it is, assume it is A, this is B, okay, assume it is C, and it is D. So the light from C, which is going from B to C, that will be extended, and it seems to be coming here. And that point we have to denote it by O dash. So the human being who will feel that the point O is not exactly here, it is here at O dash, and seems to be the depth of the water, that is not H. We have to start here and will end here. So from the surface it will end at here. So it will be H dash. Okay, so we can say H, that is the real depth, and H dash, that is the apparent depth. Apparent depth means it seems to be in our naked eye that the light ray which is coming exactly from O, but according to our eye it seems to be coming from O dash in a straight path whenever we have seen. So that is real depth and apparent depth. So here is a shift is occurred O to O dash. So this O dash, that is known as shift. Okay, so that much depth is decreased. Now the question has come, how we can able to find it? There is a big question. So let's see, can we able to find it or not? Okay, now to find it, again whenever I have to write that proof, one thing I have to mention, that proof is not needed. Okay, I have shown here because the result of the proof is needed. How that result has come, it is not needed. But as it is given to your book, so follow it, no problem. Now you see, if this angle is I, this angle will also be I, because we can say it is a alternate angle. So we have to mention that angle AOB, that is equals to I, because this is I, this is I, and these two lines are parallel. We can mention it, it is alternate angle. Okay. And if I have taken here that angle, if I have mentioned angle AO dash B, that is this angle. Okay, so this angle AO dash B, that is equal to R. Okay, why? Because these are corresponding angle. So we are using the maths of class 7 only, nothing else. Just this two line, because this DO and this N, these two lines are parallel to each other. So for that reason, we have taken this thing. Okay. If I want to find refractive index, so refractive index, if I have taken this is air, and we have already taken this is water. So as the light ray we have seen, it is coming from water to air. So it should be the refractive index of air with respect to water, because the incident ray is coming from air, and that will be W mu A, and that is equals to sine I by sine R. Achha, if I want to find out A mu W, that is refractive index of water with respect to air, refractive index of water with respect to air, if I find out, we have to take the reciprocal of it, that is W mu A, and that will be sine R by sine I. Okay, so now you might be thinking, sir, what is the need of it? Let's see. Okay, just wait and watch why we have done this thing. Now I have to take two triangles here. First I want to take triangle AOB. You see, AOB, it is a right angle triangle, and here this angle is I, that is already proved, that is alternate angle. So from here, if I want to find out sine I, so sine I means what? Sine I means if this is the angle I, so it is perpendicular by hypotenuse. Okay, perpendicular by hypotenuse. So it is AB by BO. And next thing, if I have taken another triangle AO dash B, see AO dash B, that is also a right angle triangle. So if they are right angle triangles, so if this angle, that is also, I'm sorry, it is R. So as it is R, we can write that sine R is equals to perpendicular by hypotenuse, that is AB by BO dash. Clear? So we have finding out sine I and sine R from these two triangles. Now, if I want to find the refractive index here, because refractive index A mu W, okay, see it, A mu W, that is equals to sine R by sine I. So sine R means AB by BO dash divided by AB by BO. So ultimate the thing is coming A mu W, that is equals to BO by BO dash. BO by BO dash. Now there is a problem. Okay, now we have to use a trick. What is that trick? You might be thinking that this trick is not appropriate here, but we have to use it. Okay, so the trick is, if A and B, A and B are very much closer together. So if A and B are very much closer together, then we can conclude that BO, it is nearly equals to AO. Now you might be telling that, sir, this is not right. Yes, but that is a trick we have to follow. BO, it is nearly equals to AO if A and B very much closer together. Just assume. Okay, so in this case we can take these two lines are almost equal. The length is almost equal. Similarly, BO dash is nearly equal to AO dash. Okay, so we have to replace this thing, that is A mu W, that is equals to AO by AO dash. So what is AO? See that AO represents the height, the real depth. That means it is basically H. AO dash, that will represent the H dash. Okay, so that will be the equation by which we can able to find the change of depth. Okay, so if I write it here, I'll just erase this thing. Okay, we can mention here, that is refractive index is equals to H by H dash, means real depth by apparent depth. That equation you have to remember. Okay, so if you have not remembered the proof also, that is not a problem, but you have to remember that is real depth by apparent depth is equals to refractive index. Okay, and from here one thing we have to find out, that is shift. Okay, that is shift, that is OA minus O dash A, that is H minus H dash. Okay, so H equals to real depth minus apparent depth From this equation, we can write one thing, that is apparent depth. From this equation we are writing that apparent depth is equals to real depth by refractive index. So if I put the value here, that means shift is equals to real depth minus real depth by refractive index. If I take common that real depth 1 minus 1 by refractive index. So that is our equation of shift, that how much the depth is changed, and that is the relation of the refractive index with the real depth and apparent depth. So these two equations you have to remember. If you're not able to remember the proof also, there is not a problem. Okay, I think it is clear. Now we'll go for the factors on which the shift depends. Let's see. So next thing we'll discuss that factors on which the shift depends. So before talking about this thing, we have to write the equation that shift equals to real depth into 1 minus 1 by refractive index. So by that equation, it is pretty clear for us that on which thing it depends. Number 1, refractive index. So it is very clear that as the refractive index, it is been minused over there and it is kept in denominator. So if the refractive index is increased, then the shift, it will also increase, because if the refractive index is increased, so this value will be decreased. So automatically the shift will be increased. So we can conclude the shift will be increased with increase of refractive index. Okay. Number 2, that is also very common, that is dependence on thickness of medium. So here thickness of medium means the real depth of the medium. Whenever we are talking about the glass of water, if the height of the glass of water is this, then this will be the real depth. If the height is changed to this, then the real depth will be increased. So thickness of medium, that represents the real depth. So definitely if thickness is increased, then automatically the real depth will also be increased and the shift will be increased. So thickness of the medium means the real depth. Okay, last one, wavelength of light. So in a medium, the light will be different colors. So different colors have different wavelength. In the previous class only we have learned that the refractive index of violet color, it is greater than refractive index for red color, because for violet color the deviation more, okay, and for red color the deviation will be less, so refractive index will be less. So for this case, if you see, as the refractive index is more in violet color, so here more shift will be seen. because wavelength of color, that will change the refractive index also. Okay, and if I am taking for red color, then it will be less shade. Okay, so more the refractive index, more the shift, less the refractive index, less shift. So these are the factors on which the shift of light depends. Okay, apart from this, some interesting questions it is discussed in your book. So that's also I have discussed here. The question is, if the refractive index of glass with respect to air is 3 by 2. Okay, then what will happen if I see the glass slab or glass by making an angle? Okay, so if it is 3 by 2, so we can say that real depth by apparent depth is equals to 3 by 2 for the glass. And if I want to find the apparent depth here, so it is clear the apparent depth will be equal to 2/3 of real depth. So whenever we have to see in a glass slab by making an angle, the depth should be decreased by 2/3 of its original depth. Okay, so here I just want to show you an example. You see, it is not a glass slab. Here, if you see, there is a glass. Okay, it is given, and whenever we have seen it by making an angle, if you see it making an angle, it seems to be that the writings which is written at beneath, it seems to be coming up. But if you see directly, it is at a depth. But if you see by an angle, so that writings, it seems to be coming up. So that is the reason, because the depth is decreased here. How much? 2/3. Similarly, if it is a case of water, and we know the refractive index of water with respect to air, it is 4 by 3. So for that case, it is clear the apparent depth, that is equals to 3 by 4 of real depth. That means whenever we have seen it through the water by making an angle, so the depth will be decreased by 3 by 4 of its original depth. So that is an application of refraction of light. Okay? That is another application of refraction of light. So in the previous part we have seen the depth, it seems to be changed due to the refraction of light, and here we have to see the apparent bending of stick. How? So assume this is a container, okay, and which is filled by water up to this, and you have put a stick inside it by making an angle. Okay, so that is a stick which is kept here. So stick is not seems to be straight, like it will be accurate. So sometimes instead of stick we can say a pencil also, but the story is what we have seen. We have seen it, if we have seen it from a height, then it seems to be bent or break the point through which it is entered to the water. That is also occur due to refraction of light. Why? Assume take a point O here, that is the end point. If we have taken any two light rays just entering, just going outside from this point O, then how it moves? Okay, so as they are coming from denser to rarer medium, so they will bend a little bit. Okay, but whenever we have to see it from here, okay, I have already told that we cannot able to follow the bending path. Assume it is A, it is A dash, it is B, it is, I'm sorry, it is B and it is B dash. So we cannot able to follow this bending path. What we have to see? We have to see it by a straight line. So if we have seen in straight line that O point seems to be forming here at O dash. Similarly, the portion which is inside the water, if I have taken any point through here, then also there will get an apparent position, will not get the real position. And if we have drawn that apparent position, it seems to be like this. Okay. So that is the real stick, but whenever we have seen it from a height, it seems to be breaking from the point through where it is entering the water. Okay, that is a illusion of our eye, but exactly the stick or the pencil, whatever it may be, it is not broken. That is occurred due to the refraction of light. Okay, now another example. So another example that is very interesting thing, that is known as number 3, twinkling of stars and apparent position of star. So both the things we can able to discuss separately also, but the reason are same, so that's why we have just written it in a same way. Whenever I am talking about this is a surface of earth, on the surface of earth there is a layer of atmosphere, many more layers are there, and we know the stars are at a very long distance, and whenever we have approaches from up to upward, so it is the surface of earth, as we approach upward, so what will happen, the optical density of the medium, it is decreased. So definitely here more particles are there nearer to the surface, the optical density is more. So as it is more going upward, so optical density is decreased. So if I am talking about here, a star is given. It is the star. So the light ray which is coming from the star, when it is entering from outside to here, it will bend a little bit. Okay. If I have drawn a normal, it will bend here also. If I draw a normal, it will bend here also. And assume I am the person who is standing here. Okay, to look at the star. So the light from the star is coming by this path. So as it is coming from rarer to denser, so it will move continuously towards the normal. So you see the path of the light ray bends, but we cannot able to follow the bending path. So what we will see? We'll see in a straight line, and we will feel it is the position of the star. That is known as the apparent position. So where we have seen the star in the sky, that is the apparent position. The real position is little bit of shifted from there. Okay, that is the apparent position of the star due to the refraction of light in a medium. Next thing, twinkling of stars. Why the twinklings are occur? See, whenever we are talking about the optical density, yes, as we going upward, the density, optical density is decreased, but the density is not fixed. Whatever the layers we have made, that layers are not mentioned in space. Okay, because as the temperature of the earth, it is radiated, then the optical density of the medium is changed, because the number of particles, the movement of particles are changed due to the change of temperature. So continuously the optical density of the medium is changed. So the path of light ray that is coming to our eyes, it is not come in a one path. The path of light is changed continuously. Okay, as the density, optical density is changed, so path of light, whenever the density is increased, decreased, so the path of light ray is changed like this. So that's why whenever we have look at the stars, it seems to be twinkling. Great, that rhymes. You have remembered twinkle, twinkle, little star. So the twinkling of stars, it is occurred due to the change of optical density in atmosphere. Okay, so that is another example or application of refraction of light. Okay, last application for today, then it will be over. What is the last application? Let's see. Last application is early sunrise and delayed sunset. Okay. Due to the refraction of light, we feel that we can able to see the sun before the sun rises. You must be asking, sir, how it is possible? Let's see. Assume it is the surface of the earth. So around the surface of the earth, there is a layer of atmosphere. Okay. So if I have taken that this portion is east and this is the west and this is the east. Okay. And this line we have taken the line of horizon. Assume whenever the sun is below the horizon at the time of rise, okay, means at dawn time, then what will happen? So the light ray that comes from the sun, that is coming by this way. Okay, so when it will incident here, 1 minute. Okay, so here I have given an extra layer, so let's remove it, otherwise it is difficult for me to draw. So assume the light ray is incidenting here in one surface. So we know as we move far, the optical density decreases. So if I have drawn a normal, so the light ray will bend like this. Okay, here also it will bend and here also it will bend. So like that, the light which is coming from sun, which is entering or coming to the surface of the earth by a bending path. If a man who is standing here just want to see the sunrise, when it comes to the man's eyes, he cannot able to follow the bending path. For him, the light ray is coming here. Okay, so the exact position of the sun is below the sun horizon, but according to the man, the sun has already crossed the horizon. So it is seen mainly at dawn. Why it is not seen in another time? Because whenever the sun comes here, there also there will be an apparent change and there also there will be a shifting of position. But at 12 o'clock when the sun is at top, that time the light ray is coming vertically and there is no shift. So we can say that at 12 o'clock the position of sun, it is exact, and apart from that all the positions are apparent. Similarly, whenever we have come to the west, when the sun sets, it goes below the horizon level. But if the light ray comes like this, so what will happen? It will bend, again bend, and come to the surface by this path. And if I follow this path, that will be the position of sun. Okay, and already the sun goes below the horizon, but according to us it is above the horizon. So whenever we have seen at the afternoon time, we have seen the sun, but actually the sun has gone below the horizon. So that we can able to see due to the application of refraction of light. Okay, that is all for today. In the next class, we will do some numericals on real depth and apparent depth. Thank you.